Hey everyone, Bob here. Today we'll be discussing about the vehicle gas emissions and how we're gonna control them. Emissions mean pollution for the environment and health hazard for the population. For more than 5 decades now, emissions control has improved a lot, what with the advent of new technologies. The improvement in vehicle emissions control means a lot because it means cleaner environment, cleaner air, and reducing health hazards to the population. So, in order for us to understand more about the pollutants and their controls, we need to comprehend this discussion about them. Vehicle emissions regulation started in the early 1960s, and this happened because of the smog issue in Los Angeles, California. The EPA, or the Environmental Protection Agency, has become stringent since then on the regulation of emissions. This is part of our health and safety programs. The countries like Japan, Australia, and some other countries in Europe have followed this regulation and require their vehicle manufacturer to comply with the regulation too. Photochemical smog is formed by the reaction of sunlight with hydrocarbons and oxides of nitrogen in the atmosphere. Smog appears as a light brown haze in the air. The main regulated vehicle pollutants are unburned HC, CO, and NOx. Other exhaust emissions include microscopic soot and dust particles that are small enough to remain suspended in the air. Other exhaust emissions that exist and measured during car diagnosis include CO2 and O2, but these gases are harmless. And these emissions are not pollutants but are useful in the diagnostic process. However, CO2 proved to be hazardous to the environment as CO2 contributes to the greenhouse effect. HC emissions are caused by unburned air fuel mixture is left on cooler combustion chamber surfaces when the flame front is quenched near this surface. This results in the HC emissions. Carbon monoxide emissions are a byproduct of combustion. Carbon monoxide is a deadly gas that is odorless and colorless. When breathed in, CO will combine with the oxygen in a person's bloodstream and become CO2 or carbon dioxide, which results in oxygen deprivation. The symptoms are dizziness, sleepiness, and headaches. CO emissions occur when the air fuel mixture is not completely burned. CO emissions are lowest at the ideal or stoichiometric air fuel ratio of 14.7 to 1. As the air fuel ratio becomes richer than 14.7 to 1, CO emissions increase in proportion to the richness of the air fuel ratio. So CO is a poisonous gas. In lower concentrations, it results in headaches and nausea. In high concentration, CO may be fatal for human beings. NOx emissions are caused by oxygen and nitrogen in the air-fuel mixture uniting at combustion chamber temperatures above 1,371 degrees Celsius. NOx is an air pollutant that is primarily man-made and has no natural sources of readily measurable size. High combustion chamber temperatures, such as an overly lean condition, are the main cause. NOx emissions are reduced when combustion chamber temperatures are lowered. NOx combines with rainwater to produce acid rain that pollutes the waterways, killing fish and vegetation. All three pollutants are present in exhaust emissions, whereas evaporative or crankcase emissions contain largely HC. On a typical vehicle, 60% of the HC emissions come from the exhaust, 20% come from the crankcase, and 20% come from the evaporative sources. The source of evaporative emissions is mainly the fuel tank. Since gasoline is a fuel that will readily vaporize, the more open the fuel system, the more fuel vapor can escape. The ambient air temperature also plays a part of this. The hotter it is, the faster fuel will vaporize. On some engines, the air-fuel ratio becomes richer during deceleration, and this increases HC emissions. If a cylinder misfires, the whole air-fuel charge in the combustion chamber is forced out through the exhaust system, and HC emissions increase significantly. Crankcase emissions are caused by combustion blow-by past the piston rings into the crankcase. All internal combustion engines have a small amount of blow-by. This condition causes HC emissions to enter and accumulate in the crankcase. Positive crankcase ventilation, or PCV, valve system moves crankcase gases back into the intake manifold to reduce crankcase emissions. Therefore, we need a control system in order for the gas emissions to prevent in getting to worst. Part of the system are the EGR valve, or the exhaust gas recirculation valve, the PCV valve, or the positive crankcase ventilation valve, the catalytic converter, the fuel canister, the air pump, and others. Each has its own use in reducing the emissions, which I'm going to discuss next. These are part of the vehicle which is critical in the reduction of gas emissions control. The EGR valve, which is installed on the engine, the catalytic converter, which is installed on the exhaust system just before the muffler and the tailpipe, and the PCV valve, which is installed on top of the engine and the valve cover and is equipped with a hose from PCV to intake manifold. So let's start with the PCV valve. The PCV valve usually fits snugly into a rubber grommet in the rocker arm cover with just using your fingers to install it. A hose is connected from the PCV valve to the intake manifold. An air inlet hose is connected from the rocker arm to the air cleaner. When the engine is idling, the high manifold vacuum pulls the PCV valve toward the closed position. At idle speed, the engine produces less blow-by gas, and a reduced PCV valve opening is adequate under this condition. If the engine is operating at part throttle, the manifold vacuum decreases slightly, and the spring pushes the PCV valve open to allow additional blow-by gases to be pulled from the crankcase into the intake manifold. When the engine is operating at wide open throttle, the manifold vacuum decreases and the spring forces the PCV valve further toward the open position. These actions allows the additional blow-by gas produced under this condition to be pulled through the PCV valve into the intake manifold and burned in the combustion chamber. If the engine backfires into the intake manifold, the filter and steel mesh screen in the clean air hose prevent any flame front from entering the engine through the clean air hose. An engine backfire into the intake manifold seats the PCV valve against the valve housing and prevents any flame front from entering the engine through the PCV valve. HC, CO, and NOx emissions can be converted to harmless gases at temperatures above 1000 degrees Celsius. However, it is impossible to maintain this exhaust gas temperature. A catalyst in the exhaust system containing platinum, palladium, and or rhodium allows conversion of HC, CO, NOx to harmless gases at temperatures of 300 degrees Celsius to 900 degrees Celsius. This temperature range can be achieved in the exhaust system. A catalyst is a material that accelerates a chemical reaction without being changed itself. All types of catalytic converters must reach a temperature of approximately 315 degrees Celsius to light off and start the chemical reaction that oxidizes and reduces pollutants. Catalytic converters may be pellet type or monolith type. A pellet type catalytic converter contains somewhere between 100,000 and 200,000 small pellets. The design of a monolith type catalytic converter is similar to a honeycomb. All newer model catalytic converters are of the monolith type of design. The first catalytic converters installed on vehicles in the 1970s were oxidation converters. This type of converter oxidizes HC and CO into CO, CO2, and H2O. The oxidation converter does not reduce NOx emissions, so these engines are equipped with an EGR valve to reduce this pollutant. On engines with an oxidation catalytic converter, the fuel system is calibrated to deliver an air-fuel ratio that is leaner than the 14.7 to 1 stoichiometric air-fuel ratio. This lean air-fuel ratio provided additional oxygen for the converter. The EGR system, or the exhaust gas recirculation, is designed to allow a small amount of relatively inert exhaust gas to be returned to the intake manifold and put into the cylinder with the incoming air-fuel mixture. Adding a small amount of exhaust effectively cools the combustion chamber and performs two functions: prevents NOx formation and reduces detonation. EGR function reduces NOx emissions. A taper valve is mounted in the lower end of the EGR valve that is linked to a diaphragm mounted in a sealed chamber on top of the valve. Manifold or port vacuum is usually supplied through a PCM or operated or the powertrain control module operated solenoid and vacuum hose to open the EGR valve diaphragm. Earlier EGR system relied upon ported vacuum to operate with no PCM control. For late model EGR systems, when exhaust gas recirculation is required to lower NOx emissions, the PCM energizes the EVR solenoid. Under this condition, the solenoid opens and supplies vacuum to the EGR valve. When vacuum is supplied to the EGR valve diaphragm, the EGR valve opens and allows a specific amount of exhaust gas to recirculate into the intake manifold. The PCM opens the EGR valve under certain engine operating conditions. The PCM does not open the EGR valve when the engine coolant is cold because NOx emissions are not a problem on a cold engine. The EGR valve is not open at idle because this results in a rough idle and engine stalling. The PCM usually opens the EGR valve when the engine is operating at normal temperature and speeds above approximately 56 kilometers per hour. The PCM does not open the EGR valve at wide open throttle because the flow of exhaust gas through the EGR valve into the cylinders tends to reduce engine power because a rich fuel mixture burns cooler and it is not necessary. Some EGR systems have a positive back pressure type EGR valve. These EGR systems have a PCM operated solenoid that supplies vacuum to the EGR valve. But this type of valve has an internal, normally open control valve. Exhaust gas is supplied from the lower end of the valve through a hollow valve stem to the control valve. With the engine idling, exhaust pressure is not high enough to close the control valve, and this valve remains open. When the control valve is open, any vacuum in the diaphragm chamber is bled off through the valve. When the vehicle speed reaches approximately 56 km per hour, the exhaust pressure forces the control valve closed. Under this condition, vacuum supplied through the EGR valve solenoid lifts the diaphragm and opens the EGR valve. Other EGR valves have a negative back pressure type EGR valve. With an internal normally closed control valve, exhaust pressure is supplied through a hollow valve stem to the control valve. Each time a cylinder fires, there's a high pressure pulse in the exhaust. But between these high pressure pulses, there's a low pressure. At idle speed, there's a longer time between the high pressure pulses in the exhaust and the low pressure pulses are more predominant. These low pressure pulses pull the control valve open in the EGR valve. Any vacuum supplied to the diaphragm is bled off through the control valve. When the vehicle speed is approximately 56 km per hour, the high pressure pulses in the exhaust are closer together and the negative exhaust pulses are less dominant. Under this condition, the EGR control valve closes and the vacuum supplied through the solenoid to the EGR valve diaphragm opens the EGR valve. Positive or negative type EGR valves are identified by an N or a P stamp on the top of the EGR valve housing. The evaporative system reduces the volume of fuel vapors containing HC that escape to the atmosphere. In a typical EVAP system, a hose is connected from the top of the fuel tank to a charcoal canister that's usually located in the engine compartment. The fuel tank has a dome top to allow fuel vapors to collect in the top of the tank. The tank pressure control valve, or TPCV, is located in the hose between the canister and the fuel tank. With the engine running, intake manifold vacuum is supplied to the TPCV. Under this condition, the valve opens and allows fuel vapors to flow from the fuel tank into the canister. With the engine stopped and no vacuum supplied to the TPCV, this valve is closed. If the tank pressure exceeds a specific value, as may happen on a hot summer day, the pressure pushes the TPCV open and allows the vapors to flow into the canister. An enhanced EVAP system has the capability to check for leaks in the system. These systems are used on OBD2 systems, or onboard diagnostic 2 systems. A fuel tank pressure sensor is mounted in top of the fuel tank and is connected electrically to the PCM. This sensor sends a voltage signal to the PCM in relation to fuel tank pressure. The fuel tank vent valve replaces the previous vent valve in the filler cup. A conventional purge solenoid is mounted in the engine compartment. The PCM operates the purge solenoid with a pulse width modulated, or PWM, signal to control the vapor flow from the canister to the intake manifold. Some older vehicles have a pulse air injection system. In this system, a pipe with a one-way check valve is connected into its exhaust port. This basic system's main function is to reduce HC at the exhaust by adding additional air into the exhaust to help finish the combustion process. Air is delivered from pump to a bypass valve and a diverter valve. These valves are opened and closed by vacuum supplied through vacuum electric solenoids operated by PCM. Some vehicles have a belt-driven air pump. In some of these pumps, air enters the pump through a centrifugal filter behind the pump pulley. And some new vehicles are equipped with electric air pump. And some new vehicles are equipped with electric drive air pump. So this is it for today. If you happen to like what you see, please subscribe and hit the notification bell. And thank you for watching.